Today's notes are over using the 5 equations of kinematics. So if you remember from our last notes, we kind of just talked through the different variables that make up the 5 equations. Okay, so today we're actually going to be applying those equations to actual problems. So when solving constant acceleration problems, first it's helpful to draw a diagram. So I would advise all of you to draw a diagram. And then from that diagram, then you can determine what the positive direction would be. The second is to write out values that we know, and then using those values for number 3, we're going to identify which ones we need to solve for. And then, like I said, for number 1, you're going to define the positive and negative direction, so it helps whenever you draw a diagram. And then choose an equation that involves what you know or what you're trying to solve for. Okay, so we're going to do some examples together. So example number 1, a motorcycle travels west, increasing its speed from 6.5 meters per second to 9.2 meters per second through a distance of 48 meters. What's the motorcycle's acceleration? Okay, so the numbers that we were given is 6.5 meters per second, 9.2 meters per second, and 48 meters. Okay, so the first thing we should do is draw a diagram as far as a strategy for solving this problem. Okay, so we have a motorcycle and they are traveling west. Okay, and so here's our motorcycle. It's a beautiful drawing, I know. And so they're traveling west. They have an initial speed of 6.5 meters per second, and then in the distance of 48 meters, they're then traveling 9.2 meters per second. Okay, so west is going to be our positive direction. All right, so step number 2, we're going to write out the values that we know. So our initial velocity is 6.5 meters per second. Our ending velocity is 9.2 meters per second. And then we have our displacement or distance. And it's 48 meters. Okay, and the question that it's asking in this part is, what is the acceleration? Okay, so acceleration is what we are looking for. All right, so now we need to choose an equation from our list that has v1, v2, and displacement and acceleration. So if we look back at our notes, if we find the equation that best fits this, we would use the equation 5, okay, because it has displacement, initial velocity, final velocity, and acceleration. Okay, so our equation is final velocity squared equals initial velocity squared plus 2AD. Okay, and so we need to manipulate the equation so that we solve for A. Okay, so let's first subtract v1 squared from both sides. So we get v2 squared minus v1 squared all over, and then if we divide by the 2 and the d, it would be 2 delta d equals a. Okay, so this is the equation we're going to plug into in order to find acceleration. All right, so plugging in the values, we have v2, which is 9.2 meters per second, and that's squared, minus v1, which is 6.5 squared all over 2 times d, which is 48. Okay, and so whenever we solve, we should get that a, or acceleration, is 0.4416 meters per second squared. Okay, and it is in the direction of west. Okay, for example, question number 2. After 5.2 seconds of uniform acceleration from rest, a spacecraft reaches an altitude of 5.7 times 10 to the second meters up. What is the final velocity of the spacecraft? And then what is the acceleration of the spacecraft? So it's actually asking us to find 2 values here, so we're going to treat it as 2 separate problems. So first, let's just take care of finding the velocity, the final velocity of the spacecraft, okay? So first, let's draw a diagram as part of our strategy. So we have a spaceship, my lovely spaceship, okay, and it's going to take off. Okay, and the altitude it's going to reach is 5.7 times 10 to the second meters up. So up will be our positive direction. Okay, the time that it takes, so our change in time, is 5.2 seconds. Okay, we have the displacement of 5.7 times 10 squared meters. Okay, and then it wants to know what the final velocity is, okay, for the first question. All right, so what we talked about in the previous one is that you have to have 4 of the values in order to choose one of the equations. Okay, so this is a bit tricky in this problem in that it doesn't actually state a number, but here where it says from rest, that lets us know that our initial velocity was 0. Okay, so if we look at what we need an equation that uses time, displacement, velocity 1, and velocity 2. So if we go back, we need time, velocity 1, velocity 2, and distance. So we're going to be using equation number 2. Okay. So that equation is displacement equals 1/2 v2 plus v1 times delta t. Okay, and we're going to solve it so that it is solved for v2. Okay, so when we rearrange it, you should get the equation delta t over delta t minus v1 equals v2. Okay, so plug in the values that we know. We get 2 times 5.7 times 10 to the second meters, all over delta time, which is 5.2 seconds, minus our initial velocity, which in this case is 0 meters per second. And then so whenever we solve for this, we'll get 219.23 meters per second. That's our V2. Okay, so moving on to the second part of this problem, it wants us to find acceleration. Okay, so technically we could use the value that we found for final velocity, but because we have other values that are certain, meaning that we know that that is the correct value, you should use those values before you use a calculated value, just in case there's any mistakes with your calculations from the previous problem. Okay, so we're going to be looking for an equation that uses time, v1, displacement, and acceleration. Okay, so basically we're missing v2, so we're going to be using equation number 3 for this. And so we have displacement equals v1 delta t plus 1/2 acceleration times delta t squared. Okay, so if we solve for acceleration, we'll get that acceleration equals 2 delta d all over change in time squared. Okay, so plugging it in, the values that we have, we would get acceleration equals 2 times the displacement, which is 5.7 times 10 to the second, all over our time, which is 5.2 seconds squared. And we should get that the acceleration is 42.16 meters per second squared, and this would be up. Okay, and I didn't put up for this one as well, but it would be up. Okay, the positive annotation for it gives it the positive direction as well. Okay, so our acceleration we found was 42.16 meters per second squared. All right, moving on to the final example that we're going to do today. What is the initial velocity of a car that reached 32 meters per second south in 3.4 seconds at a rate of 26 meters per second squared south? Okay, so if we draw this, they're going to be moving south. Okay, so if I'm drawing my car, okay, we want to know what is the initial velocity, so we don't know the initial velocity of the car, but they're going to reach their final velocity of 32 meters per second. Okay, and south will be our positive direction. And it takes 3.4 seconds. And they have an acceleration of 2.6 meters per second squared. Okay, so writing out the things that we know, our delta t is 3.4 seconds. Our final velocity is 32 meters per second south, and our acceleration is 2.6 meters per second squared, and we are trying to find V1. Okay, so basically the variable that we don't have is displacement. So if we look back at the equation that we'll use the one that is missing displacement. So we're going to be using equation number 1. Okay, so that equation is V2 equals V1 plus acceleration times time. So if we solve for V1, you should get, when you rearrange the equation, you should get V2 minus acceleration delta t. Okay, so plugging in the values that we have, we would get 32 meters per second minus 2.6 meters per second squared times 3.4 seconds. And so we get that it is, our initial velocity was 23.16 meters per second. And so our initial velocity was, we write it over here, 23.16 meters per second, and it was in the south, or in the southern direction.